I will start the lecture after 4 minutes. Okay, I will start the lecture. Hi everyone, my name is Anshan Mehta and I am a PMR scholar in IIT Bombay. And according to PMRF duties, I have to complete my 50 hours lecture in a year. So hence I am here to give you some tutorials on the subject dynamics and controls of mechanical systems. Good evening. So you all can chat. If you have any doubt anywhere, you can put on the chat. And how I have designed this tutorial lecture is that I have the subtopics written with me. So I will go one by one, and it will be kind of, if you haven't gone through the lectures, you can do it now, and I can brief you on what is going on the course. And also we can also find the questions or the formulas which are important, also the motivation part of it, like why we should do all those things, all which is taught in this course. Actually this is a course which is kind of a bridge course, and the importance is because it is a multidisciplinary branch, and wherever dynamics and controls are required, there actually what happens that there's an interaction between lot of fields. Alone mechanical engineering system has a lot of figures or lot of subsystems, as you can see how many subjects we have. And upon that we are also giving controls, which is generally the electronic and communication people or computer people work. Also computers are added, and so you have to know each and everything about. So we should know a umbrella view. If you have some specific problem, then we can go into details. But as this is the umbrella course, hence I will refrain it from going much into detail. We can have a relatable thing, so we can relate to some concept which actually can be good to have an analogous system in mind. But apart from that, we won't go in much into detail because it will become more confusing in that way. Now today's lecture is all about 3D rotations and how we can represent them into so everything is 3D in real world, and what we are taught is 2D, and hence we have to uh, get from this mind frame from 2D to 3D. So what happens when we go from 2D to 3D is just the notation changes, and we have to understand those notations. So we will start with the uh, uh, one and only notation which is followed in this course, and first of all we will do that, and then we will build upon the concepts of rotation, 3D rotation. Now there are some reference books which have been mentioned in the course. First one is robotics, fundamental concept and analysis, and you can find it on the Amazon also. And the chapter which are important there is chapter 2, chapter 5, and chapter 6. So I will be giving this note also, so we can have a meeting on we can have this note as a reference, because the questions which are in the assignments will also be related to somewhat like this, or so this is just the adding up of the practice which we need. And for controls we have modern control by Ogata and feedback control by Franklin, Powell and Nanny. So you can have these in the reference. Now everything comes to a practice, so this is all theoretical, but this whole uh, branch, like where dynamic and control is considered, so practice is the main thing. So the concept are built upon those practices, so hence it is strongly advised to have some practice. So hence use of MATLAB for the numerical simulation, because that is our we will say it is a primary language for NPTEL, because we have the some on ramp MATLAB, so you can easily code there and have insight about how MATLAB works. So I will advise you to start practicing the MATLAB, and wherever the exercises are there regarding MATLAB, I will be helping you with the basics. And so there is a video of basics which is created by one of us TAs, is Soumya Kanti Mahapatra, and it's freely available. So you can go there. And also this link consists of introductory video and the MATLAB program which are used in this whole course, and they're also there. So I will advise you to, if you have basics covered, then you can move on to some higher subroutines or higher programs like Simulink and Simscape. So you can directly make your own subroutine and you can use it wherever you want. Okay, so week 1 was about rigid body and coordinate systems, then positions and orientation, and then rotation matrices and their properties, then Euler angles, quaternions, and homogeneous transformation matrices and their properties. So we'll go tree by tree. So first of all, this week 1, it consists of rigid body, and coordinate system. So in the first lecture we have the notations. So before starting, I will just give you what is the motivation of this whole uh, subject. So as you know that anything can be which is manual can be automated. Okay, so now it depends on what we are automating. For example, if there is a task which we are doing 10,000 times and also in the fixed time frame or in the fixed time line, then it's better to do it by automation. Okay, but if there is a task which we only do it once, and so there is no need of automation there. So for example, if you have a dryer and if you have a washing machine, so in washing machine you wash the washing of clothes is automatic, and up to the point when you have a clothes which are wet, okay, but cleaned, but now you have to throw them from your washing machine to the dryer. Okay, now doing that is a manual task, but again the drying portion is again the automated thing. So there is a in between manual task. So if somebody wanted to create a whole automated system, what it had to do is there should be some kind of kinematic arm, a robotic arm, which can take all those clothes and put it into a dryer. Okay, so our task is to first understand what is how we can detect those clothes. Okay, so that is the part one. Then it's like by coordinate system, first you have to define the reference system. So first of all, you have to define what the positions and orientations are all about. After that, we have to uh, do the kinematics. Okay, so in kinematics we have how the things are moving and what way we are moving without the cause of the force, like what is causing it. Okay, without knowing the forces. Then next comes the dynamics, where you have to know about what is the actual cause of that force. So mainly you have to find the equation of motion, you have to find uh, the like energies. Okay, from that you can calculate the equation of motion. So we will be all be covering in this course, and finally we will have some equation of motion. Now we have to solve them. So third part is solving them, because then we will kind of make it what the end result will be, the motion from the of the end effector from the clothes, like from here to the dryer. So now coming back to um, the motivation is like third part is the control. Like now hand can do a lot of variety of things, like it can have a million configuration, million orientation, but we have to only find one which is suitable for us. So that is where we have to find the desired output. Okay, so when the desired output come into the play, then it means that you are taking whole lot of uh, configurations and you're choosing one configuration. So that choice have to be dependent on many things. So we have a linear control system in control and the non-linear control system. So non-linear control system, both are based on the feedback mechanism, and there could be two control, one is open, another is feedback. So open control is, you know, there is a linear path and you know how the end result will be, so you just superimpose the things. But non-linear control have this thing where there could be lot of other um, parameters which are affecting the system. So here what we do is we try to control it in our desired what do you call it, tolerances or desired so there could be anything which is wrong in the system, so you have to work in the desired system. Okay, now coming to the basics is like we have dynamics, then sorry, kinematics. In kinematics we have position, and orientation. So 2D is okay, but here we have to work with 3D. Okay. Now next is if the non-inertial frame of reference move. Okay, like if so once we have uh, two coordinate system, one coordinate system is at rest and another coordinate system is in motion. Okay, now the coordinate system which is doing the motion, okay, now how it will look from the rest coordinate system. So here's what we have to look at: the transport theorem. How the velocity changes, how the acceleration changes in different frames, so that we have to look. And then we can move on to degree of freedom and constraints. So in constraints, again we have two distinction: one is holonomic, another is non-holonomic. So this is what kinematics is all about. And after, just at the edge of this degree of freedom and constraint, we have dynamics, where inertia plays a major role. And so inclusion of inertia. Then we have formulation of equation of motion, or ODEs. We will write ODEs, or equation of motion. So if you have any doubt in any of these topics or the introduction of these topics, please put in the chat. I will be explaining that. Next is, once you have the equation of motion, now there are different methods to derive this equation of motion, some of which are Newton laws, then Hamilton's principle. After that, it's a Lagrangian formation, followed by, or another method is Keynes formulation. So Newton law is what we have learned in mm, our school. Okay, now here Hamilton principle and Lagrangian formulation have a similar um, like origin, and the Keynes formulation is where we use generalized coordinates. Okay, so in this course we will be looking at Newton law and Lagrangian formulation. Okay, now next is about numerical solutions. Like once we have found the equation of motion, then since we don't have exact solution of all the equations, so we sort out to numerical solutions. And in controls, we have to know the desired motion. Okay, and then we have to make the system follow the desired motion accurately, and that too in spite of the external disturbances and internal parameter change. So you would have seen mx double dot plus cx dot plus kx is equal to ft. So generally this ft is the external factors and this m, it can be also changing with time. So these are internal. Internal parameter change. So what if these are also changing with time? Now how we can perceive the stability and the control of the system? So that is one task. Now here we, in this course, as we, it is an umbrella course, and we'll be looking at only at the linear control schemes, and in that state space as well as the classical control are popular. We have state space as well as classical control. So in classical control we again have two, one is root locus and another is Bode plot. So this was all taught in lecture 1, just the introduction of it. So it was the introduction to course. We had some tree diagram, and from there everything was dependent on the kinematics, dynamics and controls. Now in the lecture 1 was very important in the format where we have given the notations. Okay, so next important thing is notations. So I will try to have these notations common in throughout the course, but let's see how much I can make that possible. So first of all, the scalars, since sir is using the digital notes, so hence the bold symbols I cannot write it in handwriting. So what I will do is I will have, instead of bold I will put a vector sign. So scalars are just shown by normal case letters and also by symbols. Okay, so those are scalars. Then coordinate systems, it is shown by curly bracket. And so scalars are lowercase or it can be uppercase also. It could be symbols, it could be alphabets. Coordinate system, it is by capital letter. And with a curly bracket. So it is defined by right-handed set of unit vectors. For example, and unit vectors are shown by hat symbols. Hat symbol for unit vector, and after that also we should know one more thing is origin. Every coordinate system comes with an origin which is shown by O, and by trailing subscript. Okay, before starting, let's talk about the terminologies. For example, this is the parameter of interest. It could be anything, it could be scalar, vector, matrix, anything. So this is leading superscript, this is trailing superscript, then trailing subscript, leading subscript. So scalars are just the parameter of interest, uh, that description I have given. If it's a coordinate system, it is shown in the curly bracket, and the unit vectors can be shown as this. So in unit vector there will be something here, this dash part, and trailing subscript will show the which coordinate system it is from. Okay, now coming to the vectors. So in vectors, Searle's notation is such that he is using the bold symbols for with the leading subscript. So here we will use again the lower case or uppercase symbols in alphabet, but with vector sign. So for example, A vector, B vector, C vector. Okay, so generally there is a V vector and A vector, velocity acceleration. And also there is one more condition attached to it, that vector should always be having with the leading superscript. Because vectors are always with respect to a coordinate system. Okay, so leading subscript are for that purpose. So leading subscript comes at this point. So let's say coordinate system A, coordinate system A, B, C, D. So these are the coordinate systems, the leading subscript. Now next is matrix. Matrix are shown by the square bracket with the capital uh, symbols with the square brackets. This is the symbol with the square bracket. So for example, A, B, C. So again, this has leading superscript as well as leading subscript. So what do a leading subscript mean is, it means the point of interest, okay, whose description it is shown. So we'll just point of description, point of interest. It could be origin of a um, coordinate system. It could be any point of the end effector. It could be anything. And leading superscript this means reference coordinate system. Okay, so then after this the course had the dot product, also it had cross product, then cross product as a skew symmetric matrix, then derivative of vector, then derivative of a matrix. So derivative of the uh, vector is just shown by the dot uh, on the top, okay, and we'll look what the derivative of matrix looks like. So that will be an interesting thing. So then again, talking about the MATLAB, there was a mention of how to use the MATLAB. So if you have any doubt, we can also solve that, okay. mm, you can also have some other programming language, but I will just suggest you to keep the MATLAB as primary language, because on-ramp is already provided, so you can have practice on that, and there is no much conversion issues. So if you have code written in MATLAB, you can easily convert it into a Python or your primary coding language. So now you have ChatGPT and a lot of AI tools to do that. Now coming to the lecture 2 part, it was all about position and orientation of a rigid body. So rigid body, first of all there is a description of rigid body, and as you know, rigid body is something where Euclidean distance between any 2 point is fixed. So if you take any 2 point and you find the Euclidean distance, so in any configuration at any time it will be same. So that is the uh, definition of the rigid body. Now talking about the representation, so any rigid body can be represented by position of a point of interest. Okay. So any point on this rigid body, its position as well as something called orientation. So let me prove that to you. For example, if you have a rigid body and we are showing that in form of a coordinate system. So let's say we have a rigid body and we are showing that in the form of a coordinate system with the origin as O. OA, this is XA, this is YA, and this is ZA. Now if you have some coordinate, some rigid body like this, and if you wanted to have the representation of it, so we can also give so this is, we are plotting that on the graph. Okay, 1 2 3 4 5 6 1 2. So if someone asks like, how can you be sure that this is the rigid body and where it's located, so you can say I have a position of point A, and just saying that won't be satisfactory, because point A can have a lot of bodies. So some body which is oriented, one second, so there could be body which is something like this, there could be body something like this or like this. Okay, there could be body which is something like this, something like that. So you cannot actually give how it's oriented. You can know that it is present in point A. So you should have additional information about the system, and that is done by orientation. Now what this orientation means is how these vectors, unit vectors, are arranged. So if you just rotate these vectors, there is a different orientation. If you rotate the vector again, there could be a different orientation. So we know that this particular orientation is only one. Alright, so that is kind of fixing the direction. So in a crude sense, if we're talking about 2D, then yeah, direction. But if you are talking about 3D, then it depends like what the configuration is all about. So we will go step by step. So position of point A is not enough. We need something called orientation. Okay. Now a best example can be dice. All right. Now if in a space somewhere is the dice and you wanted to just see what this dice is, you can have its position, like you can know its position. Let me make the dice for you. So let's say we know the position of the dice, like we can take one point and we can fix it. This is point A and we are fixing it. But what about um, what is the orientation of the dice? Now orientation of the dice is very important to the fact that the number displayed on this dice, so if you take opposite side and the face which is there, the sum is 7. Okay, so for example this one have the opposite face at 6, so 2 has 5 and 3 has 4. So this gives us a description of how the dice will look like, and if you have a point A fixed, but this could change, like this 3 can come here, 2 can come here, 1 can come here. Okay, so this gives the description of the orientation. So this is a very nice example to know what the orientation is. Hence this we can specify here only 3 points. So let's say we fix these 3, like the 1 will be in this phase, 2 will be at this phase, and 3 will be at this phase. Okay, and we know that this dice is on a table or some flat surface, so there could be only um, limited orientations, and one of the orientation is this. So we only know that the face which is facing towards us has 1, which is facing towards right, it is having 3, and which is facing towards top is 2. Generally we have interest in this region only, like what is the dice number. So that gives us the orientation. Now the 3 can also change to 1, 1 can change to 3, but still the dice top will be 2, which is of interest. Okay, so now there could be a lot of methods to show the orientation. We'll be looking at that. So this is the notes which I have prepared. Now we come to the fact that every time anything which you have to control, or let's say in this servo move, two things change about from end effectors. One is position change, another is orientation or the rotation change. Position is just a representation, and we can show it as a displacement vectors, and rotation is again a representation, we can show it as a rotational matrices. Now we have talked about 2D as well as 3D cases. So here we'll first build up the concept of projection, which is very important. So if we have some coordinate system x naught and y naught, so let's name this coordinate system A. So this A coordinate system can be shown as x naught, y naught, and there is a vector v. Now the projection of v to x axis is a, as shown in the red color. It's like if you are giving some light from the top and you are looking at the shadow. Okay, let's say we have some light coming out from this direction, so this is the up to where the shadow will be, so that is called projection. Similarly, we have b. So how to find them is, first you have to put theta under v and then make them into matrix. So this is a general rule. It can also be extended to 3D. How we can look at in 3D is by giving three independent parameters. Okay, so this rotation matrix has um, 9 parameters. Okay, and we also have 6 constraints. So 9 minus 6 is 3. So again 3 independent parameters we need. So if we have a, we have a vector, a coordinate system, which is shown as x naught, y naught, z naught, and we have b coordinate system, which is shown like this. Now R is a matrix, so it's called rotation matrix, and it's a square bracket with O as 0 as our reference coordinate system, and 1 is of the whatever the coordinate system we are finding it for. So it is like how frame 1 is rotated inside related to frame 0. Okay, so A is frame, A is coordinate frame 0, and B is coordinate frame 1. So how to find it is, again you have to look at the angles. So Z is same, so Z and Z naught are same, so hence Z and Z naught are 1. Now how Z1 is changing respect to Y is, it's not changing, so 0. Again respect to X is 0. So what changes are given in the yellow? So you can see the sign, we are putting the theta there, and then we are finding the projections. Now since it's a vector, hence each individual axis has length 1. So if you take only this line, it's like sine square theta plus cos square theta is equal to 1. If you take this line, sine square theta plus cos square theta is equal to 1. Okay, if you take this line, then the magnitude is 1. Similarly, if we will look from the column, so this is one of the properties of rotation matrix, that the individual axis has length 1, or individual column, individual row have length 1. So this is respect to z. Okay, if the coordinate system is rotating with respect to uh, z axis, so similarly if you have uh, x or y axis, the if rotation is about the x or y axis, we can have this terminology. Now this is only description of matrix. Okay, like this Rx, if I write 0 and 1, then it will be full description of it, like what this thing means. So next natural question which arise is what about the successive rotation? Okay, before that, let's complete the properties of this rotation matrix. First of all, the representation of the vector using the rotation matrix, it has the columns, and columns are unit vector, and the rotation matrix is orthonormal. Okay, so it is orthonormal also. Then determinant of this rotation matrix is 1. Determinant of yes, Raphael. Hi, Raphael. Yes, I am listening. Yes. Do you have any doubt, Raphael? I should be right triple at least. Usually, it should be right triple. What does it mean? It should be right triple. Hello. Yeah, you are audible. Slightly audible, but yeah, audible. Direction of the cosine matrix. Okay, directional cosine matrix and rotation matrix. Okay, for example, okay, I don't know about directional cosine matrix, but let me check. So this is our rotation matrix. Okay, and we can have in direction cosine matrix. I have to. Yeah, actually, I don't know. I'm also curious to find out. Let's find out. So we have direction cosine matrix versus already these rotation matrix. Yeah, nice. That transform one coordinate system to another. Rotation matrix complete. Okay, so what is direction cosine matrix? Yeah, yeah. Please. Okay. Okay, cool. I got it. Hmm. Hmm. No, no. Actually, rotational matrix is more. I will say um, more robust because if you can see, if you change this one position of this one, then you have about 9 vectors. Okay, so uh, the one can be anywhere. For example, here this one is at the uh, down position. Okay, but if it can be in the middle position and it can be on the first position also. So depending on where the diagonal it is in the diagonal, it kind of changes the DCMs also. Okay, okay, yeah, understood. No, not 9, 3. You can have 3 configuration. So all 3 come into one, right? Okay, I understood. Yeah, there's a logical doubt that is GCM as well as rotation matrix same or not? But yeah, but here we are using the rotational matrix. Okay. Now, what about the multiple rotations? Oh, we were at the properties, right? So it's a orthonormal and determinant should be equal to 1. And also the inverse is same as transpose. Okay. Inverse is same as transpose. So these are the properties. And if you talk about the eigenvalues, then there are always 3 eigenvalues, and the characteristics polynomial is cubic, and there is a invariance of these eigenvalues, which is a product of these eigenvalues. Again, the magnitude of each eigenvalue is 1, and 3 eigenvalues come from mathematics, like you can derive them also. So there is a special case when eigenvalues are a special case. It's worth mentioning. Eigenvalues are +1, -1, -1. Okay. So this is something called singularity, and it is a headache to the numerical computation because computer doesn't understand this, and so we have to make a bypass uh, regarding this. So then there was talk about the Rodriguez family laws also. So you can find the element of the rotation matrix easily with that, given in the um, lectures. Okay, coming to the successive rotations now. So we have an example here where it is we are rotating frame 1 about 45 degree z axis, like about z axis, and frame with respect to frame 0, and then rotating 45 degree about new x axis. So let's see how it will look like. It will be, so instead of this theta, here is 45 degree. So about z axis it is rotating, and after that again another 45 degree about new x axis. Now new x axis is this. So about this red line, the whole coordinate system is again changing 45 degree. Okay, So it is very hard to visualize, but you can do that easily in the MATLAB, how it is going on. But our aim is here to find the successive rotation. So we know that resultant rotation is just the product. So this is our resultant resultant rotation. Also we know that the this type of rotations, successive rotations, are not commutative. So it's like if you mm, if you do 45 rotation about first x-axis and then new z-axis, then it is not same to 45 degree z-axis and then 45 about new x-axis. Okay, so one of the properties, so that means that order of rotation is important. Okay, now first of all we are looking at from 0 to 1. So I is given as this identity matrix. Looking at the diagram, so this is called kinematics diagram. This drum shows the rotation. If you're looking at the first rotation, which is rotate about the z-axis, so we can find it out. And then second is rotation matrix, first frame. You can visualize this in matrix in the MATLAB also. Let's stick with the this is 1, this is 0, and square bracket. 0, this is 1 square bracket, 1 2 square bracket, hmm. This is product. So this is equal to this, which is again eventually equal to this. Now our aim is to reach to the end effector from the base frame. Okay, so from the the frame which is at rest to the frame which is successively moving, like from one coordinate system to another coordinate system. So here comes the concept of Cartesian manipulator, and then we have articulated manipulator, followed by spherical manipulator, as well as cylindrical manipulator. So you can have different kind of manipulators, and we can have different rotation matrices, successive rotations. For example, Cartesian uh, means that how frame 1 is rotated with respect to 0 frame, then from 0 to 1 to 2, then 2 to 3. So it gives us the idea of that only 3 angles are required, so we call them as Euler angles. So before jumping to that point, let's write down the properties of successive rotation. First of all, it is not commutative, and the order of the rotation is important. Then coming back to, so you can have the idea about Cartesian and articulated manipulator. We are in this course, we have the knowledge of only Cartesian. Okay, we'll come to the other manipulators in further part maybe. Okay, how much it's needed. Okay, now there is one area where we can go is how we can represent the orientation. Another is how can we can represent the position. Once we have understood how the position work, okay, which is like next part of this next week program, we can then come to a homogeneous form, homogeneous transformation matrix. So it is also in the similar line, and there can be another other um, representation of the orientation. So before going that, let's go into homogeneous transformation matrix. So it is shown like this. Again, I will just change the because I wanted to keep the notation same throughout the course. So this is a rotation matrix which we have learned, and this is homogeneous transformation matrix. Okay, yeah, we were at Cartesian manipulator. Then another example is articulated manipulator. So look at these examples. Then spherical manipulator. Just change this matrices to, or change this notation as unit. So these are all unit vectors. Okay. After that, after that we looked at the Euler angle. So these are three rotations. Which completely so in this case we can have a 12 possible ways. And it is also minimal representation of orientation of rigid body. Now these three distinct axes are called tight Bryan angles. Okay, now you can have an example of an aircraft where we have so let me draw an aircraft. So this is an aircraft. heading in this direction. Now it can have coordinate system as this. Okay, so this one is going inside. One is along the direction of this aircraft, one is 90 degree to it, and one is actually going inside the screen. Okay, so it's along this wing. Now if this aircraft it rotate about this axis, the top axis, then it's called yawing. If it's about this axis, then it's called rolling, and if it's about this, then it's called pitching. So you can know how the aircraft is behaving just by knowing these angles, and that those are the example of the Euler angles. Again, the order is important, and algorithm is there if these angles are given and you have to find the orientation. Now there is also example of spinning top, so we call them as spin precision, spin precision, and tilt. So these angles are in spinning top. These are also example of Euler angle. We will cover them in the future class. And also there is a robot, Puma 560 robot, that is also given in the book also. You can refer to the book, and that is based on X, Z, Y, Z Euler angle. Now after that, these are called the uh, so there are two different category. One is body fixed rotation matrix, and space fixed rotation matrix. So distinction about this: now they are both different, but they're also related. Okay, how they are related is rotation matrix obtained from body fixed XYZ from space fixed XYZ rotation is same as rotation matrix obtained from z y x, like opposite, okay, and vice versa. So if you just interchange the uh, or the reverse the order, then we get that is the uh, body fixed. Now there was also pictorially representation of that, so you can refer to that. Then there was example where 3D numerical example, um, for XYZ and ZYZ body fixed Euler angles, and there is a MATLAB code there. Then there was another example 3D numerical where XYZ and ZYX space fixed rotations were there. Again the MATLAB code is there. Now apart from that we have other representations as well. So something called Euler parameters. Description is given as like it is 4 parameters with one constraint. One benefit of it is we have no singularities here. Okay. After that we have quaternions. Four parameters. So again here we have no singularities in the quaternions. So if you wanted to make a chart of all the given item, we have starting from rotation matrix. First of all we look at parameters, like how many parameters are there, then how many constraints are there, then singularities, and application will give after that. So rotation matrix, then Euler angles, then Euler parameters, quaternion. The parameters which we have is in rotation matrix is 9, constraint is 3, singularity yes. Euler angle we have 3, 0 constraint, still singularity is yes. Then Euler parameter is 4, constraint is 1, no singularities. And this is quaternion is 4, this is 0, this is no singularities. Now quaternions, application of quaternions in other fields. Quaternions are extensively used in motion planning. So this course is all about. Then altitude control. Of spacecrafts. Then computer graphics. And animations. Quantum mechanics. Now we can convert one representation to another. For regular cases. Okay, so we just have to beware of the singularities, and apart from that we can easily convert, not easily, like using coding. So this is what was contained in lecture 2. Now lecture 3. So lecture 1 was about 23 minutes, then lecture 2 was about 2 hours long, and lecture 3 was 20 minutes. So in lecture 3 we had homogeneous transformation matrix. So it gives combined translational and orientation. Okay, so before, could you please tell line of the codes professor used to demonstrate motion of the solid cube? Yeah, actually I also don't know. I also wanted to find it out. So because I will be performing those in MATLAB. Okay, so I will ask to him, those codes. Yeah, after getting it, maybe next lecture I will take a short MATLAB session also. In that we can talk about what codes we are using. So probably the already two courses use this example. Really interested. Yeah, I will find it out. I am also interested in that actually. How because sir also mentioned it's in MATLAB code, and wow, yeah. So that will be a huge thing because to visualize mainly. Yeah. Okay, I will just put in task list here to ask sir regarding dice example. No. Dice example codes. Once check into that links which you have provided. Okay, if you can access those codes from there. Otherwise I will surely find it out. I have just written it in the task list. Okay, moving on. So before moving on to homogeneous transformation matrix, first you have to see how the positions are marked. So positions are also marked in a similar manner. Now displacement vector is shown like this. uh, Let me just quickly convert this notation because this was the old notation which I have learned. Okay, so this was the rotation matrix from uh, of frame n relative to frame m. Okay, and these are all vectors, unit vectors. Now d the vector, so we will show it like this. And x, y, z are the scalars. Okay, so hmm. So displacement vector can be shown as d vector of m with respect to n. No, opposite. uh, this displacement vector can be represented as d vector of n, the point of interest, with respect to m, and it can be shown in the three uh, scalars: x with x of n with respect to m, y of n with respect to m, and z of n with respect to m. and vector sign. So in the figures, these x's are there. So in your mind, just replace them by hat. Okay, just add hat to it, because then we will be following a proper notation. Otherwise, the color has been used, so no issue in that regard. No, yeah, d vector. Sorry. D vector. Okay, I still don't understand this. Delete. Also in notation, let me add this sine and cosine also. Like sine theta I is shown as s theta I, and cos theta I is shown as c theta I. Okay. So now if you want to find the vector of 2 with respect to 0, then that is not by multiplying or rotating, that is actually lumping them into the homogeneous transformation matrix. So whenever you are finding the displacement, so we also have to consider the rotation matrix as well. So hence that combinedly is known as homogeneous transformation matrix. Okay. Now in different examples, you can see as Cartesian manipulator how we can find the displacement vector. Next is articulator manipulator. We'll go into detail of them. Okay, just look at the figure and correlate with that, and if you have any trouble you can ask in the next tutorial. But we will be covering these four type of manipulators in detail, I hope. So this is our homogeneous transformation matrix. Homogeneous transformation matrix. So this is the example, like this, then D the vector, okay. So there is a shortcut also. We can use Dinavit Hartenberg method in assigning HTM. So you can follow these rules. I think page. So next in the course we had seen properties of homogeneous transformation matrix. In particular, we have seen inverse, then two successive transformations, then n successive transformation. Then again, example of dice. Then also property of this transformation matrix can be related to a screw. Okay. So let's solve this question. First understand the diagram. It's a little tough to understand, but look at the colors and then correlate with that. So we have x naught, y naught, z naught as our frame 0, then x1, y1, z1 as frame 1, then x2, y2, z2 frame 2, and x3, y3, z3 frame 3. And the distances are shown a1, a2, a3, a4, and also thetas are given, theta 2, theta 3, and d1 is also given. So values are as given like this. Now we know that if we draw this so it's given x is equal to 1, and then a2 is equal to 2, so 1 is this, then a2 is this, x equal to 1 of 1 is 1, y is equal to 2 of minus 1 plus 2, 0, and then z is equal to 1 plus 1 is equal to 2. So what we are finding out here, Nearly 0. Vector D. Oh, okay, this vector D. Vector D is shown, yes, the last one. So yes, we have to provide this D like from the starting only. So it's like 0 is also moving with D1. Again, actually I didn't read the question. Yes, yes, we have to find the D. So uh, first of all, let's find this D first. 0 D vector 1. theta 2 c theta 2 0 s theta 2 0 1 0 and 3 second matrix. 1 second. Okay, so we have 0, then from 0 to, so this is green, or green. Hmm. Okay, so we have frame 0, then frame 1, 2 and 3 with everything known. So it is actually from part of spray paint, and that can be attached to end effector. And when the links lengths and joint variables are set as shown, where is the spray paint can located and in what direction is it pointing? Answer by drawing the spray paint can be provided 0 frame. Okay, so 0, there is this spray paint, and then we have to find so spray paint is on frame 3, and then we have to, you can see there is a symbol of the spraying, and then we have to find the from 0th position. So hence we can find out by multiplying the HTM of successive HTM. So we have taken from 0 to 3 is equal to from 0 to 1 first, then into 1 to 2, then 2 to 3. And we have defined the HTMs. For each HTM we have to define the displacement as well and individual rotations. So we have done that, and finally we can have this as a complete solution. Now there is another question. Show that here is shown is here is the rotation matrix, and can why so we have to prove it is a rotation matrix or not. So if you look at this line, so second matrix, are you meaning 1 to 2 are this one? One zero zero. Oh, okay, this one. Okay, this one matrix. Oh, this I have mentioned you. There is a there is a different type of orientation we can use, representation. So we are here using this kind of representation. Just read this, okay? This example. Just go at the starting, and so there is a way by which we can put it into a coding thing where at what angle it's changing from what. So we can multiply it using INT matrix, and changes in the INT matrix, it can give us the same matrix. So as you can see, the starting matrix is same. in this in this the starting matrix is just same. Okay, like cos theta 1 to cos theta 2, and whatever the second matrix is, that is giving the combined effect of the rotation matrix. About which axis, actually it's dependent on which axis the rotation is happening. So the second matrix is giving that. Okay, as we are above time now, so hence we'll quickly complete. So 0.8 square plus 0.8 square is not equal to 1, so hence not a rotation matrix. I will upload this document into and I will share the link. Okay guys, thank you. If you have any doubt, you can ask in the next tutorial class. So I'm stopping the recording.